Okay. I assume it's time to start now. Thank you for coming. My name is Steve Skeena. I'm a professor at Stony Brook University in New York, and I'm going to talk, generally about word and graph embeddings over the course of this lecture and the stuff before it. What I'd like to start out with is first telling you who I am. So I am a computer scientist. I am a data scientist, okay, in some sense. I like to work on, applied machine learning, trying to use data for trying to, learn things, discover things. I've had, let me see how this works. I've had a bunch of collaborations in bioinformatics with biologists, so I know how biologists work, and social scientists. I work a lot in text analytics and NLP. We once had a startup company that tried to do sentiment analysis from text. And that's something that involved data analysis. And these are things that kind of drive what I'm going to be trying to teach here. The other thing that I would like to point out just from people is I like to write books. I don't know if have any of you ever seen any of my books? Oh, okay, good man. Okay, so I have an algorithms book some of you may have seen. But in the context of what we'll be talking about here, I have a book on data science that kind of covers how I think data science kind of, what's involved and should be. And anybody who's interested in data science, I encourage you to check out this particular book, which is called the Data Science Design Manual. This book is what I use when teaching my own data science class back at Stony Brook. And if you're interested in my data science class, I give you the link to all the lectures from my courses, some of which this is going to be drawn from. Any questions or comments so far? Okay, before I get started in what I'm going to actually teach, I want to make sure that, this is the first time I've ever taught at a summer school like this. And I know that many of you are from different countries, different fields, different things. I like to make jokes and tell stories during my class. And if I say something that is dumb, I want you to accept my apology at the beginning. I want everyone to feel comfortable and happy in here. If there's anything I say that bothers you, come back afterwards to tell me and I will apologize. Any questions about that I think is understood? Let me give you an outline of what I hope to cover during the 3 sessions that we have here. I'm going to start by today's class. I'm going to be talking about primarily word embeddings, which are a very fundamental topic in NLP these days, and have been for several years. But I think that there are very interesting things associated with word embeddings and what you can do with them that are not completely obvious. And I think I'm going to like to talk about that as my first session. For my second session, I'm going to talk about how you do machine learning on graphs, or in particular, how you turn graphs data, network data, to features for machine learning models. We're going to talk about something called graph embeddings that we were involved with, making popular, and show how you build these graph embeddings, show how you can use these graph embeddings, and talk about other aspects of these graph embeddings, how you deal with graphs that are changing, when there's edge insertions and deletions and things like that. And I'm going to try to talk about sort of nearest neighbor methods for trying to understanding what graph embeddings mean. And I think that's kind of an interesting thing. And my plan for the third session okay, is by that time I should know you people better. And we'll figure out what actually is interesting or not interesting to you guys. And so I have a bunch of topics from when I teach my data science class that will, if there's particular interest, we'll focus on that. Or if I decide I'm interested in something, we'll focus on that. But that's kind of my ideas here. Any questions about the outline or anything like that? Okay. When I teach in my own class, it's very important to me that there be kind of participation and discussion, okay? And this is especially going to be true because you people are from strange lands compared to where I usually teach, okay? I don't know if any of you, actually, are people able to understand my English okay? Or is this clear, not clear? I have been told before that sometimes when I teach in other countries that they like my English because I sound like the gangsters from movies. You've seen a lot of American movies where you have gangsters, and this is this. But it will be best if we end up, I would be happy if we don't just cover all my slides or even most of my slides. So if we end up having discussions about things that you're interested in, about your data sets, your problems, things like that. Any questions about that? Okay, so I was going to, the group's a little bit too large for me to ask everybody who they are, but I do want to get, before we get any further, just an idea of who you people are. So first of all, where is it, how many of you would you say are, if I'm going to say industry or academia, which one of you, you'd have to pick one, the universities or industry. How many of you are industry people? Okay, how many of you are university people? Okay, that's good. Okay, and how many of you of the university people, how many of you, I want to know, are master's students versus PhD students? How many of you are master's students? Okay, and how many of you are PhD students? Okay, so that tells me something. And as far as where you guys are from, just to get a quick idea, how many of you, I'm going to do this at a continent level, just to make sure I understand. How many of you are from the Americas, one way or another? Nobody. How many of you are from Europe in one way or another? Okay, this seems like it. Do we have any people from more exotic places? Asia, Africa, Australia? Okay, so this is good. And of the people from Europe, how many of you are from Spain? And how many of you are not from Spain? Okay, so this, I think I understand it. Okay, so I think I understand what you people are about. And I'd like, but I do want there to be questions or comments here, because I think that this is going to work wildly better if we end up getting some kind of discussion together. Any questions or comments? Somebody? Okay, good. So what I want to first talk about today, I'm going to want to have us talk a little bit about, I'm very interested in kind of, if you want to think of it, feature create construction, unsupervised machine learning feature construction, okay? That you would like to be able to take an arbitrary data set and build some kind of features or some kind of thing that is useful to do a lot of different tasks on it. That's kind of what interests me. Today we're going to talk about ways of doing this with language data. And I guess the first question I'd like you to see is, if you wanted to teach a computer what the word cat meant, what is the right way to do it? Okay. Actually, how many of you have what you would call NLP backgrounds? How many people don't have NLP backgrounds? This is good. No problem with that. That's good. Okay. So how would you tell the computer what the word cat meant? Now, you might have thought that that it was cat was, you learned about words. I don't know if you guys can't see anything here, right? So this isn't going to do that. But you might think that a word is defined by its definition in a dictionary. So the word, the definitionary dictionary of what a cat means, maybe that would be useful. Maybe you might imagine that there are, I guess you can see this pointer here, logical definitions of what a cat could be. A cat is an animal that has 4 legs and goes meow, okay, and stuff like that. You might think pictures are useful. What I want to convince you of today is that the thing at the bottom is what a cat is the right way to represent a cat to a computer. What is this thing? This thing is a word embedding. Okay, it is a vector. In this case, I think it has something like 64 dimensions. Each one of these dimensions is a number. Okay, and the more positive it is, the redder it is. The more negative it is, the bluer it is. So this is a drawing of a 64-dimensional vector. And what we would like to do is the key idea of word embeddings is to reduce what words mean to these numerical vectors. Any questions about this so far? Any questions anyone wants to talk about? Okay. So how could we build a representation of what the word cat means, or what any other word means, okay? From unsupervised text. You're given all the text on the web, you're given Wikipedia. How do you figure out what the word cat means? So one way to build these vectors is, or a vector would be useful if you could use them to tell the difference between real phrases and what I'm going to call corrupted phrases. It's easy to get text from the web that is, intended to communicate with people, is properly written text. Now, suppose I took a phrase like this and I substitute one of the words at random, okay? Who here knows German? Are there people who know German? Okay. So one of these phrases is from text I got on the web, okay? And one of them is something where I randomly substituted one of the words with one of the few German words I know. Which is the real phrase? Is it S or S prime for my German speakers? Can you tell?
Second one is not right.
What?
Second one is not right.
You think the second one's not right. Is that a concurrent? That's right. Achtung is one of the only words I know in German. I substituted it in the middle. Any of you who couldn't answer this question, probably you didn't know German. Okay? If you didn't know German, this was probably a hopeless task. Okay? So if you could build a model that could tell the difference between which was the real phrase and which was the broken phrase, okay? That model knows a lot about the languages. And what's great about this kind of an approach is that you're starting from only training text that is real, that's right, okay? And cleverly, normally to build a machine learning model, a classifier, you need to have positive examples and negative examples. By doing this kind of thing, this gives you a way to construct negative examples. And if you can build a model that can tell the right one from the wrong one, clearly in the course of training that model, it's got to learn a lot about the language, okay? And this is sort of the idea behind word embedding models like, any questions about this? Let's maybe start out. I'd like to hear from somebody. I know I'm maybe going too slow, but people, yes.
The first sentence, I
Sorry.
don't get the meaning because it has not been finished.
It's not complete.
Okay, you're telling me that, so one thing that you're saying is, I gave you 1, 2, 3, 4, 5, 6, 7, or 8, maybe 8 or 9 words, but I didn't give you a full sentence. Okay, and you're telling me you can't tell that you're 100% right. Okay, in these kind of things, there's a fixed text window. If you're going to build a model, you want the model to have a fixed size text window in terms of the number of tokens. And if the word sentence isn't complete, maybe you truncate it, maybe you look in the middle of the sentence. You guys were still able to tell which was right and which was broken, even though it wasn't a complete sentence. You don't know what the whole sentence means, but for the ability to tell truth, broken or non-broken, that you're able to do with what you got. Any other questions or comments? Okay, good. So what is the standard way to, the most famous way to build these word embeddings? These word embeddings was built by a program called Word2Vec, okay, which was developed by people at Google, Mikhailov and others. And what they basically did was you were given they built a model, a neural network model, not very deep, okay, but that would try to be a classifier model to tell broken or not broken. You would feed at the lower level the word embeddings you have so far, the vector describing each word. Originally, these would be random. You could come up with random vectors. But when you give it a question, examples and try to say broken or non-broken, when it gets it wrong, it does machine learning magic to refine the parameters of this network. So it's going to get it right next time. Okay? And in the course of doing this, it's going to build up vectors. You give it a new phrase, you pull out the appropriate word vectors for that one, for those words, and you will get, it will eventually learn these things. Okay? So what is this showing me? This is a picture of word embeddings when we built word embeddings at some point. If you look at the vectors that you get for horse, dog, and cat, they all look very similar. Why is that? That's because they're all animals, okay? I have a pet horse. I have a pet dog. I have a pet cat, okay? Changing one of these words to the other one shouldn't produce much of a difference. They're both going to be kind of right, okay? If you look at the countries, India, China, Azerbaijan, you should be able to see that, that the word embeddings are the same, are the same. Note, so it should be clear, and same thing with numbers and colors. The way to think about these things is not that there is one dimension for this is a color, but there's kind of a pattern of dimensions where all the colors are going to be grouped in kind of the same place. And that's the way to think about these things. Any questions? So when you see one of these word vectors for cat, you should be saying, sure, that's a cat. It looks just like a dog. And that's the way to read these things. Any questions or comments? So what could you do with these word embeddings? Okay, and the original thing to do with word embeddings had to do with NLP and the ChatGPT-like things. In fact, if you think about the way we're training these word embeddings, I think I forgot to mention this. Okay, everybody's in love with ChatGPT these days. Notice that ChatGPT is kind of trained in a similar way as these word embeddings. Okay, in that, what do? You give it ChatGPT to train it. You gave it a sentence, and you said, predict what the next sentence is. That was kind of the criteria that was used in training this thing. It's sort of the same thing like here. I'm going to give you the real sentence. I'm going to give you a garbage sentence. Tell me which one is right, okay? So both of these things are being trained in a unsupervised way by trying to guess something that is missing. In this case, in my case, what was missing was the middle word. Here, what's in ChatGPT, it's missing the sentence to come. But the same basic principles hold. Okay? Any questions? So what's interesting about this? So we first got interested in word embeddings when it came to, we wanted to build a system for doing basic NLP in every language that we could. And for us, the notion of what we mean by every language was whether or not that language had a Wikipedia written in it. Okay, so for us, again, with a lot of these problems, getting access to data becomes the big problem. One thing that was great about Wikipedia was that you had, over 100 languages with decent-sized Wikipedias. You had all of the same annotations. Hyperlinks in all the languages look the same. You have, titles look the same in all the languages. So we could basically train a model for all the languages once we could train it on any one Wikipedia language. And the first step of this was, of course, to construct word embeddings on the language for the words for any particular language. So what language are people speaking? I think we decided you guys are Spanish. Here, when we trained a Spanish word embedding, okay, what were the words that were closest to dentist? Okay, you could think of these word embeddings, they're like points in space, okay, and I've been talking about 64 dimensions, but maybe 300 dimensions, depends what you want. The closest words are probably those that have similar functionality in that language. And they were all jobs that people did, okay? And that's the kind of thing you would like to see. If these word embeddings are good, nearest neighbors tell you should be very similar things. Any questions about it? Okay. This is a map of English that we built by looking at the word embedding. What is this? Every dot on here is a, is a word, okay? I don't remember how many thousands of words they are, okay? We took these in 64 or 300 dimensions, I don't know how many dimensions we had, projected it down to 2 dimensions, and colored them according to what the part of the role in speech those words had. So all the last names for people were here. All the first names for people, I believe, are over here. Okay? States in the United States are here. Countries are here. Cities are here. Does everybody get the idea that these word embeddings really kind of organize the language? Okay? And nearby things may have the same meaning. They have similar meaning. They may be used in different ways. What's great about this is that the embeddings kind of capture this, okay? And once you've got meaningful notions of what words mean, you can then build higher level tasks on them. Our interest back then was in analyzing news streams. You have news is written about people, things happen to people, things happen to organizations, things happen in places. You would like something that could read a text in any language and identify what the people, places, and things are. Okay? People, places, and organizations. And how could you do this? Well, once you have trained word embeddings, you now know what every word means. This is a useful feature for a model that's going to, given a sentence, going to try to figure something out. If you have examples of things in sentences that you know are people, maybe they are things in Wikipedia that were hyperlinked to pages that are about people, or places that were hyperlinked to things that were places. Okay? You get training data. And now the problem of building a classifier that would identify, is this word part of a person, a place, an organization, or something else? This now becomes a straightforward thing to do, and you can do it in all the languages. And this is why we were excited about that. Any questions or comments about this? Yeah. Oh, I see. Wow.
What about the words that have different meanings, like one word but have separate meanings? Do they have like different word embeddings?
Okay, so now let's think about, it's a good question. What do you do with a word like, I always for some reason use the word run. Run is an example of something, you're used to this. I remember hearing that stockings had runs in them. There's something like that. So a run could be a noun, a run could be a verb, okay? How would you tell this? Now, the thing to know is, notice that the different parts of speech are not really labeled in our input text. We were given raw text. We don't know which sense of the word run is there. So what's going to happen? This mechanism will give every word its own one representation. And for run, that means it's got to cover the verb and the noun and whatever else it's going to be. So how would that look like? Well, notice we're dealing with 64 dimensions or 100 dimensions or 300 dimensions. There's lots of different ways you can be close to each other, to things. You could be close, run could be put into a place where it's close to the verbs and maybe close to the nouns also, okay? So the answer is it would be better if we knew in advance what part of speech every word was and gave it a separate token. So if I could have analyzed my text ahead of time and said run-noun, run-verb, that would have been helpful, okay? But in general, we ignore that, and that still works pretty well. Those of you who know about modern natural language models, like BERT or something like that, these produce context-sensitive word embeddings. So the embedding you get in a sentence is going to change from sentence to sentence. And that in that case, if you were using it as a noun, it's going to look different than when you were using it as a verb. But in the mechanism we're doing with it, we're lumping all parts of sense, and generally things still work out pretty well. Any other questions about this? Okay. Fair enough. Now, when we're talking about these multilingual embeddings, there's one other, let's say, background to think about. If you think about what I did here, I trained separate word embeddings for every one of these 100 languages. And what the dimensions mean are going to be different between different languages. Okay, this is one thing that it's an unsupervised thing. The model's figuring something out. Okay, if I looked at the numbers in Hungarian and I compared them to my numbers, the representations of my numbers that I showed you in English, what would happen? Because they were trained independently. 1, 2, and 3 in Hungarian are still going to look very similar to each other. But there is no reason why 1, 2, and 3 in Hungarian are going to look like 1, 2, and 3 in English, because they're trained independently. Does everybody get that idea? So if you wanted to build something for multilingual applications, sometimes this is fine. This didn't hurt us when we were training 100 different models for 100 different languages. Sometimes you would like to have a world where, wouldn't it be great if gato in Spanish had the word embedding that was very, very similar to cat in English? Okay? How would you be able to manage something like that? One way would be if you could train on a text corpus where you have phrases with a mix of English and Spanish. You could imagine a world where, what if I knew that cat and gato were translated? Maybe you could imagine, oh, well, look at me, fine, here's my pet, gato. You could imagine substituting words that you know are the same. And that would kind of bring the spaces together. Or you could try to do a some kind of rotational warping of these dimensional spaces. So suppose I have an English language space and I have a Spanish language space, and I have 10,000 words that I know are translations of each other. You could imagine solving some kind of a linear regression to predict the Spanish embedding for any English language word, okay? Try to rotate the space so cat goes close to gato, and dog goes to perro, and stuff like that, okay? So there's different ways you could kind of so you can either have embeddings that are separate, or you could have embeddings that are unified across languages, and there are a couple of different ways you could think about doing this. Any questions about this? Yeah?
So you have the second method, and you can try to transform it into like to have a similar embedding for two different languages. So for the second method, when you try to transform the embeddings to a different language, so in, for example, my language, marriage in Norwegian.
Wait, what do you speak?
I speak Norwegian. So marriage
Norwegian, yes.
in Norwegian could also have a different meaning as poison, but it doesn't have that meaning in English. So how do you deal with the different meanings?
Okay, so again, the idea here, and I'm going to use this trick later in the talk also, so maybe I'm happy to talk about this. Again, does people kind of get the idea of what we're trying to do? We have two different spaces. We know they are representing their languages kind of the same. We have mappings between words and their translations. So the goal would be, can we find a way to warp all of English to Norwegian such that the translations of English words are close to their corresponding Norwegian one? Now you're saying, what if there is a word in Norwegian which has other senses? That it means run and jump out a window. Okay, I don't speak Norwegian, but let's say that was true. Okay? Well, if we have enough different examples of translations and we warp these things, those two words are not going to coincide perfectly when we do them. You would expect that the words that have multiple senses are not going to be put in quite the same place. But in principle, the same basic thing should still work. You wouldn't want that word in Norwegian to be exactly at the word cat, because it does have other meanings. And that would presumably happen when when you do this translation. If you have enough words, you're not going to find a perfect mapping, but a useful one. Is that good enough? Okay,
Yeah, that's perfect.
good. Any questions here? Okay. And again, there's all kinds of things that you can do with, some interest in, sometimes people want all the languages in one space. If you have embeddings of languages where all the words are in one space, this is something that can be very useful for translation. If I had English warped to Norwegian, and I wanted to find what the word for cat is in Norwegian, how would I do it? I would look to see where in this embedding the English word for cat is, and find the nearest Norwegian word, and that's a good candidate to be the word cat. How do you say cat in Norwegian? Cat? See?
It's different pronunciation, but quite similar. So it's like cat in Norwegian, cat.
Okay, fair enough. Any questions about this or stuff where we're sitting here? And this I maybe don't want to talk as much about. Okay, any questions about word embeddings and how you use them for language kinds of things? What's interesting is next step I'm going to talk about is about training word embeddings. We talked a little bit about how you train them, but there are a bunch of different algorithms for this that are kind of clever. And I'm then going to talk about some applications of word embeddings that are kind of interesting that I hope you'll find interesting. So what is the idea behind training word embeddings, or why word embeddings kind of work? And it turns out that that this dates back philosophically to a work by a linguist named Firth, okay, who famously said, "You will know what a word means by the company it keeps." This was what his kind of distributional hypothesis is. Linguists care about words, okay? They care about language. That's why they are linguists, okay? And, the question of what does it mean when words are similar? His sense was, it's just basically that when words are used in similar context, okay, they're going to be similar. So what is this showing me? This is showing me part of a word co-occurrence matrix. What does it mean? The rows are words. The columns are words. And there is a count of how often this word appeared close to the other word in a text database. We can define, does close mean within one word, within 10 words? You can define what close means. But if we look at this kind of data, aardvark never occurred close to any of these words, which kind of makes sense. If we look at it, what words occurred close to digital? Well, data and computer and result occurred. Information occurred even more close to data and stuff like that. It should be clear that given a word co-occurrence matrix, this is going to tell you a lot about what the words mean. It tells you what are the company that a word would have. And so one way you might think to try to build one of these embeddings is to start out by taking the entire vocabulary of a language and build a vocabulary size by vocabulary size table of how often these two words occur next to each other. Now, what's the vocabulary of a language? Does anybody have a guess for their favorite language? How big do you think your vocabulary is?
50,000.
50,000 is a good guess. Now, notice it's not a well-defined answer. Is Skeena, my last name, a word in English? Okay. Now, it's not in the dictionary, but if you look at enough web text, you're going to see it, okay? Maybe people complaining about my book or something like that, okay? So the question of, but 50,000 is a good number. A matrix that's 50,000 by 50,000 is a very big matrix and unwieldy to work with, okay? One thing to note here also is that in this case, most of the entries will be 0. Because most words never are seen next to other words, okay? But still, this idea of the co-occurrent matrix is conceptually an interesting thing. Any questions? So one thing that you could do is, for any word, if you wanted to try to come up with a feature vector for what does apricot mean, one possibility is to just take the row of that matrix associated with apricot. That would give you data about, it would tell you something about how frequent is the word apricot used. It would tell you about what words are associated with apricot. What's bad about that? Okay. One is it's going to be a very long vector, which is, how long is it going to be? As big as the vocabulary size. So you said 50,000, okay? It's also going to be very, very sparse. Most of the entries are going to be 0. And so if you want to build a machine learning model where you've got a 50,000 dimensional data thing, this is hard. This requires a lot of data and stuff like that. This is why we're going to be interested in sparser representations of words. Any questions? So what did word2vec do? Again, I told you a little bit about word2vec a few minutes ago. Word2vec, remember, was a world where I said, well, I didn't actually talk about exactly how word2vec itself worked. I gave you the idea that there was this network model to try to tell whether something was broken or not. The truth is that there are kind of two different optimization criteria that word2vec would use. One is probably closest to what we would think about, which is something called the continuous bag of words, or CBO. No, actually, I'm going to take it back. One of them, let me make sure I get this right. Right. Actually, let me see if I've got this wrong. The two conceptual differences are, one, you have you're giving it as input the words around one that is missing, and you try to predict the word that is missing. The second is you're given a word, you're told that this word is in the middle of a string of 4 words, and you try to predict what are the 4 words that were around it. This would seem like a much harder problem, okay? I think that's called, if I've got this right, that would be called skipgram. The other one is called CBO, or continuous bag of words. But there are 2 different optimization criteria you could use here, both of which, if you built a good representation, the better your representation for what words mean, the better you could predict what was missing, the better you could predict what the other words in the sentence were, given just one of them, okay? And giving the appropriate loss function and stuff like that, that's how word2vec would work. Any questions? Another idea here that, came up, that follows more directly from our matrix idea, is this idea of coming up with a low-dimensional representation for what words mean based on factoring matrices. Okay? What do I know? Suppose I have a matrix, an n by m matrix, let's call it A. This is my data matrix. If this is a word embedding thing, I've got a set of rows for every one of these verbs against every other word. It would really be, in this case, n would equal m. But suppose I can take my matrix and factor it into the product of 2 matrices, okay? So that A is going to be roughly equal to B times C. Now we know when we multiply matrices, the inner dimension of the 2 matrices has to be the same. If we force that inner dimension to be small, this is going to give us, together, B and C are going to approximate that matrix, okay, and compress the representation. And one of these terms is going to give us a small feature vector replacing the matrix. Let me show you the picture. This is kind of obvious. I mean, it's obvious once you see a picture. Here you've got your data matrix. Suppose I could factor my data matrix. So, in this case, my data matrix were the counts. How often is this word used next to that other word? If I could factor this matrix into if this was an n by n matrix, if I factored it into an n by k matrix times a k by n matrix, okay? What's interesting about this? Just this single matrix here is going to have a row for every word, and it's going to have only k columns. Each row here tells you a lot about the corresponding row of the full matrix, okay? And so another approach to building word embeddings would be based on factoring matrices. Okay, I don't know if I'm seeing people get tired. I don't know if it's probably me, but maybe the time of day. How many people see what I mean by this matrix factorization idea? Or are there any questions or comments about it? Okay, you've probably seen matrix, we may have seen matrix factorization in other contexts, okay? But it's a very powerful idea, okay? If you can do this kind of factorization, then you get, you know, especially if you can specify what the number of columns you have, you get, you know, you get k-dimensional representations. In the case of words, it was an n by n matrix. So either the the first matrix or the second matrix gives you word embeddings. Maybe you would add up the two, the row vector and the column vector, to get your word embedding. There's different ways you could do it. This kind of idea is often used in when you have words and documents. There'd be a row for every word. There'd be in the vocabulary, there's a column for every document. There's a count for how often that word appears in that document. Factoring that matrix into things tells you for each word, you're going to get a k-dimensional vector. And also for each document, you're going to get a k-dimensional vector. It gives you a way to approximate what a document means or what a word means. Any questions about that? Yeah.
So for the column where we have documents.
Okay, hold on. Mr. Mike is coming.
So for the column where we have the documents, it's going to be like the name of the document, the name of the book, or the genre of the book? Like this is an algorithm book, so we have a column for algorithms book, or we have like schema for algorithm as a
Okay, so what's going to happen if we think about this as a word document matrix? He's saying, what do the document vectors mean?
Yes.
Okay? The word vectors, by now you've been convinced about, means similar words should be close to. If the embedding is close to each other, the words probably mean the same thing. Similarly, in a document vector, if you have two documents which are similar, they should mean the vectors should be close to each other. So I would imagine if you have an algorithms book and another algorithms book,
so like
these two document vectors are going to be very, very close.
Okay.
If you have an algorithms vector book and a book about football, it's not going to be so close.
All right, cool.
If you have an algorithms book and a book about computer networks, it's going to be kind of closer than the football book, but not the algorithm book.
All right, thank you.
Okay, so that's the interpretation here. Yeah.
This reminds me to the procedure. Sorry. This somehow reminds me to the procedure of dimension reduction.
This is exactly the procedure of dimension reduction. Okay. So, what ways do you know about doing matrix factorization? You probably know about SVD, singular value decomposition, or principal component analysis. These are classic matrix factoring algorithms. There are other matrix factorization algorithms, okay, that are out that have interesting properties, like guaranteeing that none of the values will be negative, for example, okay? But note that this is an approximate factorization. There's many different ways you might factor it. A given matrix cannot necessarily be perfectly factored into an n by k times k by n thing, but you can, by some criteria, approximate it, and this can produce an interesting embedding. Any questions? Good. Now, when you want to use this matrix factorization kind of approach to on word frequency counts, it should be noted that working from the raw matrix frequency data is going to cause certain kinds of weirdnesses. What is weirdness? Well, first of all, common words are going to get big numbers next to other words, right? So the word the, is the word the going to be associated with aardvark? Yes. It's going to be associated with just about everything, right? Partially because there's going to be spurious hits just because high frequency words are more likely to get some counts next to something else just because it's got more tries. You know, a word that occurs 1 billion times is going to be in 1 billion windows. A word that occurs 10 times is only going to be in 10 windows. So there's one problem of frequency, and there's a problem of spurious correlations. Quite often, words are going to appear next to other words just by chance more than that they really have a real association. So what is rather than working on the word count matrix, if you want to build a good representation of what words mean, you'd like the counts to be counts that are serious counts, that measure how, strong connections between words. So one measure that's important is this thing called positive pointwise mutual information, PPMI. And what is the idea here? If we look at this term, this is saying if we want to get a strength for how associated is word W from word C, okay? One way that you could do it is as follows. You look at how often word W and word C occur next to each other or near each other, and divide that by the frequency of word W and the frequency of C. What would it mean? If this was just a random language where people were emitting words uniformly without any kind of higher order structure, the number of times W and C would be next to each other depends on the probability. If there was independence, it'd be the probability of W times the probability of C. If there is dependence between the words, they should occur next to each other more frequently than they would under the independence model. So the PPMI matrix takes our counts and instead reduces it to what is the overrepresentation of the number of pairs compared to independence. And it takes the log of that, and it takes the larger of the overrepresentation and 0. So what does this mean? If words W and C occur next to each other only by chance, then we would expect that the probability of W and C being next to each other is the probability of W times the probability of C. This matrix has the property that it's going to look at words that occur, the words that occur by chance will get zeroed out, and you get a very sparse matrix that looks like this. Okay? Any question? Here you have some word count data. Should the word cherry appear next to the word computer ever? In a big enough corpus, it's going to happen. I spilled cherry juice on my computer, okay? But when you grade it by the pointwise mutual information criteria, these counts are going to get 0, and only the words that kind of mean something real will get substantial counts to it. Any questions about that? So one of the famous word embeddings that are pretty good, that if you end up caring about word embeddings, you should know about, is something called the glove embeddings. This stands for global vector, I think that's what it is, global vector. That's why they call it glove. And these are trained by explicitly building this, this PPMI matrix and factoring them. And so if you need a good English language embedding, the glove embeddings are one of my favorite good English language embeddings. Okay? Any questions? There are also other techniques for building word embeddings that are kind of interesting. There is a famous set of embeddings for many, many languages called fast text. This was built by some people at Facebook. Okay, it's now they're Meta or something like that. That they did the following technique. They, instead of training on full words, okay, trained on k-mers of characters. Okay, so let's think about this. Suppose you were given, we so far verified, is there anyone here from China? Okay, so I'm sorry about this example. But as far as I know about Chinese, there is not much in the way of tokenization. If I looked at a Chinese word in Chinese text, I would have a hard time knowing where each word started and where each word ends. Is this a fair statement? Okay. So if I had to build, how would I deal with a language where I don't know even how to chunk what the words are? In English, you feel pretty good about chunking words. You know, they're the things between spaces, right? So what was the idea here? The idea here is that instead of learning an embedding for a whole word, they're going to learn embeddings for k-mers of characters. Here, k was equal to 3, okay? And we talk about sliding windows. Learn what blank space WH is, what HER means, what ERE means, what RE space means. You could imagine using the same technologies we've talked about. We can learn what each one of these things means. What do they mean? What does WH mean? Well, I don't know. But first of all, the fact that it's capitalized probably means that it's something that belongs at the beginning of a sentence. When you have a word, what does ing mean? Does ing mean anything? That's a 3-mer. I think ing to me means something that goes at the end of every gerund, right? Running, you know, fighting, thinking, right? So what is the idea here? The idea here was, let's learn a representation not of words, assuming we know how to tokenize them, but let's learn the representation of k-mers. And everything that I've said so far should clearly be easy to apply. And then if I want to know what where means, I've got to combine all the k-mers for that word. How can I figure out what where means if I know what WH means, HER means, ERE means, and RE means? Maybe I could take these embeddings and add them up and average them. That would give me a sense of what where means, okay? And this may sound dumb because, you know, I'm adding like her, according to this now, is not, would mean something in the middle of where as well as, you know, the pronoun her, okay? But the claim is that there's going to be information gathered in all these words. The context around them are going to be where the word where appears. You can build up interesting embeddings from the corresponding k-mers. And this is especially true for words that are not actually in the, you know, that you didn't think of as being in the training data to begin with. In many languages, words are made from by adding, you know, prefixes and suffixes to them to create other. German is a bad example here, right? What do I know about German? I don't know much about German, but I get the sense that words are kind of stringing many words together, right? So either I define my vocabulary as the union of all combinations of things that have appeared between blanks, but that's going to be a huge vocabulary. Or I try to determine representations of individual parts. And fast text kind of works from this idea of individual parts, okay? and it's very, very good. And for stuff that we do, which I'll talk about soon, the interesting thing is that they have embeddings for many, many languages. So when I need word embeddings on lots and lots of languages, this is where I go. Any questions about the embedding strategy or why this might be a good thing? Any questions? No. Okay. Fair enough. And, when you say which of these methods produces the best word embeddings, the answer is somehow it depends. Okay, how would you tell? Well, one way that people judge this thing is that they give them a bunch of different tasks. One task that is a good way to, an interesting way to judge how good a word embedding is. There are, I'll say, linguists who have asked, armies of people to say on a 0 to 10 scale, how close are certain pairs of words? Okay? So if I tell you that tiger is so similar to the word tiger that I give it a 10, how similar is tiger to cat? If I ask you to this, how many people think tiger is a 7? Tiger and cat, maybe it's a 7. If you said, what's an example? Stock and jaguar. Are those similar words? No, they're not. Jaguar's an animal or a car. Stock is, I don't know, I guess maybe something you buy and sell. So you could imagine that they ask a lot of people, give me a 0 to 10 cents for this word pair, how similar are they? This is the word similarity 353 task, okay? And and for similar kind of tests, the question is, could you build a model given the 2 word embeddings to predict what the humans are going to say, how similar these words are? Okay? And, this is the kind of thing people would do. This was a table on a bunch of word embeddings on a bunch of tasks, and it shows in dark which one did they think was best. Which group do you think produced this table? Was this done by the word direct people, the FastX people, or the glove people? Okay, this one was done by the glove people, but in this particular case, so gloves are good embedding. They're all useful embeddings and stuff like that. Any questions? Okay. Now, you might want to say, what if I wanted to build a representation for something bigger? What if I want to know what a sentence means? Okay, I now know from these word embeddings, you should believe you know what words mean. How can I figure out what a sentence means? Okay, and one possibility is you take all the words in your sentence, maybe deleting the, and other stop words that are, too frequent to count, and you just average them together. If it's a 300-dimensional vector and you've got 10 words in the sentence, you produce a representation for what the sentence means by averaging the 300, for each column, the 10 words in it. Okay? If you do this, you get an embedding, and similar sentences are presumably going to have closer embeddings than those that are not similar. Okay? This sounds a little bit hokey, but actually it works reasonably well. Okay? It should be clear that if instead of sentences, I ask you, what do books mean? Well, if I'm adding up 100,000 words and averaging them, it should be clear that what I'm probably just going to get is noise at that point. I'm going to get everything's going to be near 0. But for short enough texts, this can give you some idea of what words mean, what sentences mean. Okay? Although, what sentences mean depends not only upon what words are in there, but what the order of those words are. This is an example I really like, in that this is something like 8 or 9 sentences where all the words are the same. The only thing, all the words except only, okay, are in the exact same order. Wherever you slide the word only, you get sentences that mean something different. Okay, did everybody kind of see that? Okay. Like for example, he only told his mistress that he loved her. Okay, he told her this, but he didn't show it. Okay? So you should be clear that if we do something where we're trying to figure out what sentences mean based on averaging the words, okay, all of these would be treated the same by that embedding technique, even though they mean something different. Okay? So there's limits to how good simple averaging for sentence embeddings would be. Any questions about that? I think that's probably clear. Any questions into that? So modern language models, okay, do other things to try to make better word embeddings. These languages, models like GPT-3 or GPT-4 or BERT or T5, these are not simple neural networks, but very complicated neural networks, where on the bottom you feed it the characters of the sentence, and it munches through it, and it produces, in this case, again, a vector for every word in the sentence. But the vectors here mean something about how that word appeared in context. Okay? And when you do this, this gives you a way to figure out, this case now, the representation for each word depends upon what it means. Using this to build a sentence representation would hope to distinguish between all of those examples I gave you with only. Okay? So modern language models can be used to come up with embeddings for sentences or reasonably large chunks of text that are more powerful than just averaging the word embeddings. Okay? Any questions about that? These language models, how you deal with larger text, things like that. Okay, good. Any question or no? Okay, what I'd like to now talk about, though, are applications of embeddings. And these are a couple of applications that came up, a bunch of applications that came up in research that we did. And you'll see a couple interesting things. These are going to be, what's going to be, I think, interesting about my applications here is that they're about doing what's supposed to be something about data science. They're going to be about trying to understand the world, not so much understand individual pieces of text. And they're not going to be the kind of things that you build a large language model for. So, I mean, these large language models are amazing things, the ChatGPTs and stuff like that. Here we're going to be looking at simpler things that, but we're going to be interested in studying things like how vocabularies rather than studying text, okay? And I'm going to be interested in how language works. And these are the things that I'm going to talk about as my applications. So one thing we were interested in was, could you tell when words change their meaning? Okay? So what do I know? I am an old man. When I was growing up, the word gay in English meant happy. The word has changed its meaning over the years, okay? Now it means homosexual, okay? Sort of. And could you figure out when words change their meaning? Okay? I am sure in whatever language you guys speak, over the period of time, words have changed what they mean. Is there any examples you guys have of a word that you know about in your favorite language that changed its meaning over time? Putting you on the spot. Yeah?
Yes, in Arabic we have a word called cream. Cream in Arabic in the 50s and 60s means cream. Yeah. So in Arabic, in 50s and 60s, the word cream is qishta of Arabic, in Arabic, and it means cream. But right now it means something cool, something nice.
I see. Okay, okay. Cool is probably a good word in English at that point, right? You know, back, 100 years ago or 200 years ago, cool was what? Cool was like this room, okay? They did a good job air conditioning it, right? But cool then at some point became, yeah, this is cool, okay? How could we figure out when words have changed their meaning? So what is this an example? This is a picture that we built in a paper of ours where we looked at what does a word mean? What did the word gay mean over time? Okay, and you can see in this picture at least, okay, you can see gay drifting from happy and cheerful to homosexual. How did we build a picture like this? Okay, well, what do we know? Word embeddings capture what words mean, right? What if we were training word embeddings on text that was produced every year, okay? You would, for example, let's think about, again, why do words change meaning? Sometimes they pick up other senses. Your notion of Kareem as being cool and versus milk-like substance, okay, is about picking up another sense. Sometimes they change part of speech, sometimes they don't, stuff like this, okay? And words today on social media change even more quickly than in the standard dictionary sense. So if you wanted to know what text means, you need to know whether words have changed meaning since you built your model. Maybe would they have a different meaning in the past or not? So what was our idea for how we could tell when words change meaning? Well, are people familiar with Google Book Ngrams? Okay, one thing that's a lot of fun for you is to go type in ngrams.google.com. And what did they do? Google knows everything. Google has scanned books, something like 20% of all the books ever published. What they did is they built up a data set for every, they will build up a data set of how often every short phrase has appeared in books every year from like 1800 to date, okay? And this is a very, very useful thing for seeing how words go in and out of fashion, right? There's old-fashioned words, there's new words. The word computer wasn't used very much in 1850. You would expect to see a graph of this thing. Google's Book Ngrams tells you what the frequency of each word, each 1, 2, 3, 4, or 5mer is in books published in a particular year. What did we do? We took these Ngrams as text to train on. We could build a model of what the words meant in books published in 1900. We could then train word embeddings on books that were trained in, that were written in 1905. Train word embeddings on books trained in 1910, ... Now we've got word embeddings that capture what the meaning of each word was in books published in that year. If we want to compare these embeddings, they were trained independently, we've got to find a way to put these things in the same dimensional space. This was like what happened with word translation, right? To get Norwegian and English into the same space. What we would like to do now is to say, can I take the words from 1905, what they meant, and warp those things so that they are what they would look like in 1900. The same technique applies. The word cat in 1905 is the same word cat as in 1900. I can use this to train to do a regression, to rotate the space of the newer embedding to the old one. I could do the same thing for 1910. Warp that to the embeddings in 1900. By doing this, I could put all the different versions of words, okay, in each year's, the appropriate year, for each year. I can put them into one space and then measure what is the distance between the embedding in 1900 of the word gay and the embedding of in the year 2000. And depending upon what that distance is, bigger distances probably mean that the word has changed its meaning. And if you do the statistics in the right way, you'd like to be able to figure out whether or not some of that shift is going to be because of just chance and noise and training. You'd like to be able to measure when were there statistically significant changes. Okay, again, you have to first do this rotation. That's what I'm trying to talk about here, to bring the spaces together. Once you've done that, you can now look at what are the words that have moved the most over the course of these 100 years. And these we found very, very interesting. Gay was, I think, the word that moved the second most in this time. Tape, at one point, meant something sticky. Does the word tape mean now? It means record something. At least at one point, it meant record something. It meant, I'm going to tape something. My favorite word that changed, sex was once something you were, then it was something you did, okay? And my favorite one was diet. Diet once meant what you ate. Over the course of the 20th century, diet eventually became what you didn't eat. I'm going to go on a diet. I'm not, and so this is interesting. So these are fun. Does everybody see how you can, in principle, figure out which words have changed their meaning because embeddings capture what words mean? Any questions about that? Yeah. Okay, sorry, I think it might be.
Yeah, so are there any similarities between trends for words? Like slang, for instance, are they going to be developing very similar changes to their embedding?
Okay, say this again. I didn't hear you.
Okay, is it better now? Or is it...
We'll find out.
Okay, are there any good patterns or are there any distinct patterns in the trends of between words?
Okay,
slang, for instance, do they develop in a very similar way in terms of their embeddings?
Okay, so it's clear that in this case what I'm measuring is how much for an individual word I'm detecting which words move the most. You're, I think, asking a higher level question. Could I look at this and try to maybe predict which words are likely to change? Okay, or come up with a theory or what? Maybe that's not what you're asking.
Or more so that are there any set patterns of how individual words might change? Like slang, for instance, will they follow very similar trends in how embeddings develop? Will they gain some attributes and then slowly fall off, for example?
Okay, right. So I think that what you're right is, I think you're talking now about the mechanisms for how words change.
Yes.
And typically it is developing another sense of the word. That gay was originally happy. It started being used with respect to, sexual preference. And then eventually the gay meaning happy dropped off. People stopped using it for that as much. That's probably the way that these things would drift, often by coming up with another sense and that sense eventually being dominant. If that's not what you wanted, talk to me afterwards. Okay, that's good. Okay, let me just talk about another, I'm going to talk about 2 more applications, and I promise I'll send you home. But this is kind of interesting. We were interested in gender and how language is used. Okay, so we agree that that historically, okay, certain domains of the world were male domains, and certain domains in the world were female domains, if you go back long enough. Let's take a look at it. Career, would this have been, if you went back 100 years, 200 years, is that a male domain or a female domain? It would have probably been more of a male domain. What about family? Okay, that would have probably historically been a more of a female domain. It's not how the world should be, but maybe it was. Okay? And sometimes language reflects these things. Is there a way to which we can see if language is becoming less gender, encoding less in the way of gender bias with time, or not? So what could we do? Well, using the same trick we talked about before, okay, you can imagine training word embeddings on every particular 20-year period. You could now say, if I wanted to say is family words, husband, wife, children, okay, house, I'm going to make these things up. Those are family words. Are they more male or more female? Well, one thing you could do is pick some words that are definitely male, like the word man, okay? And pick some words that are definitely female, like let's say female or woman. And you can now ask, are the family words closer to the generically women words or the generically male words? This is about computing distances between things, right? If I want to take a look at, is the word family closer to the word man or closer to the word woman in embedding space? In an ideal world, it would be equally far apart. But in general, what we have seen is in the older cohorts, word embeddings trained on old languages. Go back. What happened? Okay. The male words for career and science were much more associated with men. The words arts and family were much more associated with women in 1800. But what's interesting, the good thing is, as we look at embeddings trained on more modern cohorts, you can see that everything, line 0 would be there's no different gender preference. And as you can see with time, what you're reading with these things is indeed converging on a more gender agnostic language, okay? And so in some sense, what's great about these word embeddings, they provide you with some kind of a time machine to how did people think or talk or something like that back in the past. Any questions about that? And you can see this again, so long as we think words mean what vector, what you call it, so long as words mean what their vector is, that's good. One last example, and I think this you'll find fun. Okay? Notice that word2vec can deal with any data that is a sequence of tokens. It wouldn't surprise me that there's stuff that you guys have that is data that is sequences of tokens that are not words. It can still figure out what those tokens mean. Okay? So what did we want to do? We wanted to figure out what names mean. Okay? Names tell a lot about you. They can tell you typically what your gender is. Okay? They're male names and female names often, not always. They can tell something about your ethnicity or nationality. They can tell you something about how old you are. There are some names in English that were popular 100 years ago that you wouldn't get caught dead naming your kid these days, okay? There's, you know, so recognize that the name tells you a lot about a person. Not everything, obviously, but something. How can we figure out what names mean, okay? And there's a very important principle in sociology called homophily. Homophily is a notion of love of self. And it means that people tend to interact with people like them. Okay? So what does this mean? If you're an actor in Hollywood who's a big star, who do you think your friends are going to be? Probably actors who are big stars, right? If you are a Chinese leader, who are your friends going to be? Probably other Chinese leaders, okay? If you are a young graduate student in a Spanish university, who are your friends going to be? Probably relatively young Spanish people, okay? So we were in a project where we had data on email contact lists. We knew for 57 people, we didn't look at the actual data, so I know there's no privacy thing here, but we knew for every person, in some sense, who their closest friends were and that they sent them the most email. Okay? Now, could we figure out what names mean from these email, name parts mean from this? Well, suppose I encode the people you send email to by just concatenating their names together. You send your mail to John Smith and Mary Jones and Harry Shapiro. I don't know who it is, but you get the idea. You can just build a string by concatenating names. And then ask yourself, what do the names mean? If you have a lot of strings of names, you can train word embeddings on those name parts. You could figure out an embedding for what John means, and Mary, and Pablo, and Martinez, and anybody else. So what is this? This is a map of the world's namespace, where we took all the most popular first or last names that appear in the U.S. Census. Okay, and we colored them by what ethnic group they appear most frequently in the U.S. Census. And when you cluster this thing, what does it mean? The names where people are more likely to be Caucasian, most likely to be Caucasian, are colored in pink. The ones which are Hispanic, okay, are colored in yellow. And here I'm zooming in on this. Does everybody see here that these are, you guys are Spanish, some of you. These are Spanish-like names. We're able to look at these things. Naturally, their embeddings are closer, because if your last name is Zaragoza, you are probably sending your mail to other Spanish-speaking people, okay? And we come up with these features. Asian language names were interesting. Notice that there's not one Asia here, but two Asias. Why is that? Well, one of them was South Asian and one of them was East Asian, okay? And that these names kind of capture, kind of what's going on. So when you do this, you get feature vectors for every name, okay? And I'm going to rush because I think I'm out of time. Is this correct? Okay, I promise I'll send you home. You can use this, first of all, for building classifiers of names. And so we have a tool that's based on this that's used for to classify names by nationality for research purposes. And you want to study discrimination in a group. Does this group have the same balance of name ethnicities that you would expect from people in something else? But there are all kinds of different things you can use. This, I promise, will be my last slide. To show you that names have meaning, we built a model to try to predict the lifespan of somebody by name. If all I know is somebody's name, can I predict how long they're going to live? Now you look at this and you say, that's impossible. right? But obviously it's not impossible. Who's going to be expected to live longer, Mary Smith or Joe Jones? Does anybody have an opinion on that? Who's going to live longer? What, Mary Smith, right? Because, you know, women live longer than men. There's also differences within subpopulations and things like this, okay? So what is this doing? We trained on data from the Social Security in the United States Death Index, which gave us 85 million people where we knew who they were dead, we knew how long they lived, we knew basic demographics on them. And we built models, trained models to try to predict how long they were going to live based on standard demographic features. What ethnic group are you in? What year were you born? Are you male or female? Okay? And then we added these name embedding features. And when we did this, we were able to predict, basically, the average lifespan of people with about 2 months less error using the name embeddings than just the demographic variables. Now, why would this be the case? Well, name embeddings capture finer demographics than just what you would see, you know, by the major ethnic groups in the United States, okay? Norwegians tend to live very long in the United States. I don't know if you guys know that. Okay? This would kind of pick up, if you learn on that, maybe you'll learn that good things happen to Norwegians, okay? Any questions about that? I'm hoping this is inspiring, that you can take data, you can build these vector representations, and move on from that. Any question quickly? I'll be here to talk to anyone who wants, but I do not want to force people to sit after the deadline. Any question that's needed? Okay, I'm going to ask one question here, just to double check. Somebody who's counting, I'm not looking. Was the level of depth that I did today did I move too fast, too slow, or about right? Who here says too fast? Somebody count. Who here said too slow? Who here says about right? What was the answer? Right? Okay. In that case, next class, I'm going to be doing something right about building graph embeddings, feature vectors trained on graphs and networks. Have a good night, and I'll see you guys tomorrow. Some of you. A few more. Okay, thank you. Hi there. Yeah, sure.
I'm working with embeddings.